Well, good day, and thank you for joining us today for ITIF's event, Scale Matters, Understanding the Economics of Global Semiconductor Innovation. I'm Stephen Ezel. I'm the Vice President for Global Innovation Policy here at the Information Technology and Innovation Foundation. Well, semiconductors truly represent the heartbeat of the modern global digital economy. It's a $600 billion industry that enables $7 trillion of downstream global economic activity annually. And of course, everything underpins everything about our modern economy, from artificial intelligence to electric vehicles and mobile phones. The costs to compete in this industry are indeed staggering. America's semiconductor industry is the world's most R&D and capital intensive, with the industry reinvesting 35% of its revenues each year back into R&D or capital investment. Designing a cutting-edge 2-nanometer semiconductor chip today costs $750 million, while the cost to construct the latest 2-nanometer or less semiconductor fabs is approaching $30 billion. In other words, it requires enormous scale for companies to successfully compete in this industry. And that means that companies must be able to sell their products into global marketplaces so that they can recoup their tremendous upfront cost of R&D and investment. And for the United States, it's also imperative to recognize the stark reality that it costs about 30% more to build and operate a semiconductor fab in the United States than it does in East Asian nations. That's a combination of wage rates, regulatory permitting policies, agglomeration effects that make it cheaper to build in Asia. But that's why it was so important that the Bipartisan CHIPS Act tackled this cost differential with a combination of a 25% investment tax credits, $39 billion in loans, and $11 billion in financing for public-private R&D investments for American companies to design and build the next generation of semiconductors. In short, nations that wish to lead the world in semiconductor design and manufacturing must have a laser-like focus on ensuring that they offer the most attractive policy environment and business environment to support this vital activity. So that's what we're here to discuss today: the economics and finance of global semiconductor innovation, how global competition in this important industry is likely to unfold over the remainder of the decade, and what the United States needs to do to remain atop the field. Before I introduce our panelists, let me note that we'll be taking your questions at the end of our session through the Slido application. There's a link you can submit your questions on the bottom of the webpage. So our all-star panel today features first Mike Demler. Mike is a semiconductor technology analyst and strategic consultant. He's got more than 45 years in the semiconductor industry, started at the great firm Texas Instruments, was most recently an analyst with the Lindley Group, but he is the author of numerous articles in publications such as the Microprocessor Report and co-author of the recent Guide to Processors for Deep Learning. Mike, thanks for being here. David Lamb is senior advisor with BRV Capital Management. David holds over 25 years of global technology investment and operating experience in the semiconductor industry. He's a leading venture capitalist in the sector. He serves on the board of numerous semiconductor firms. David's a real industry expert as well. He holds an MA in organizational sociology from Stanford and an MBA from the MIT Sloan School of Management. From the corporate perspective, delighted to be joined today by Nick Montella. Nick is Director of Global Government Affairs for TSMC, the Taiwan Semiconductor Manufacturing Corporation, where he leads their strategic policy initiatives in areas such as international trade, export controls, and supply chain resilience. Nick was previously Director for Policy for Japan, Korea, and APEC at the U.S. Chamber of Commerce. Nick holds a Master's in International Affairs from Northeastern University. Last but not least, delighted to have Eric Breckenfield with us. Eric is Director of Technology Policy at NVIDIA, where he leads their policy issues related to semiconductor supply chains and AI. Eric was previously with the Semiconductor Industry Association here in DC, and also a AAAS Science and Technology Policy Fellow for the White House's National Nanotechnology Initiative. Eric holds a PhD in Materials Science and Engineering from the University of Illinois. So it's a wonderful panel today, a great mix of perspectives. Thank you for joining us. Mike, I'm going to turn it over to you to get the conversation started here.
Great. Thank you, Stephen. I think I'll start by aging myself a little bit more. It's hard for me to admit it, but my interest in semiconductor technology started 50 years ago when I was an undergrad engineering student at the University of Buffalo. And I assembled some circuits, soldered together transistors and wires. But when I read that engineers could actually design the circuit and have it fabricated in a raw piece of silicon, that just blew me away. I was determined that that's what I was going to do, and I had the privilege of doing that for many years and then covering the industry ever since. So I think it gives me a somewhat unique perspective on how the industry has developed and grown over that time. When I started, we didn't have personal computers. Computers were mostly mainframes that were in large air-conditioned rooms, and users would have to log in through some sort of a dumb terminal. Intel had created the first microprocessor just a few years earlier before I got started. And if you want to look back and have that starting reference point, that chip had 2,000 transistors. And if you look at today, the latest AI accelerator from NVIDIA has around 100 billion transistors. So that's a factor of 20 million times. And imagine the scale of the effort, the number of innovations and technology breakthroughs that had to occur in design and manufacturing to achieve that. And now if you look at the industry today, innovation has really never been greater throughout the entire ecosystem, and not just at the big companies that we're talking about, but throughout. And I know we'll get to VCs and startups later, but there's a lot of funding activity, a lot of activity all throughout the small companies. There's 75 companies in Q4 that all together had received over $3 billion in funding. And so that's an interesting point on the economics of the industry, because it now takes hundreds of millions of dollars or maybe even billions to get a new semiconductor company started. But even though there's a lot of activity all throughout, there's always just a few companies that are at the top of any segment because of the complexity and the cost. The ones that achieve the largest market share tend to attract attention, and sometimes there's groups of regulators, policymakers that might think that they've achieved that leadership through monopolistic practices. But I have to say that I don't think that's hardly ever the case. Besides just examining the cost of what it takes to lead in the semiconductor industry, you look at the amount of talent to overcome these technological challenges, the resources to access the global markets. You can see why in the last 50 years, very few of those original companies have survived. If you take, say Intel and PC processors as an example. At the time, other companies created processors, but they most eventually fail, and for a number of reasons. The ecosystem was very early on in its development. You have a first mover advantage. You need to develop the software and the hardware. And there's really only so many platforms that the developers can support. And Intel happened to be the best at it, and they're the ones that survived. In fact, I remember that I was working on my master's degree at Texas Instruments, and they developed a processor, and they developed a personal computer. And I used it to actually write my master's degree thesis. And it overheated. They couldn't compete because they had inferior technology. It was unreliable, and they eventually had to exit the market. A company as successful today as Texas Instruments. So, that's just one example. There's others throughout other parts of the industry. The initial microprocessors, looking from how manufacturing technology has advanced. It was really relatively simple at that time. I don't want to minimize the accomplishment, but the original integrated circuits were more like shrinking a printed circuit board onto a piece of silicon. Today, we're measuring the dimension of the transistors in angstroms and billions of a meter. We're manipulating materials at the atomic level. So that's why building the manufacturing facilities, the foundries, the fabs, now cost $30 billion. It just takes that much scale to do it, and you have to have very large customers that are reaching very large markets to support that. And besides PC processors, the same thing happened in other segments, in smartphone chips, in AI processors, in networking. And so, yeah, the dominant leaders emerge, but you look at the industry overall today, there's actually more companies in the semiconductor business than there ever were. Just in the last few years, you mentioned this microprocessor report and our guide to deep learning. I've covered more than 50 startup companies just in the AI processor segment alone, and there's other parts of the industry that are growing as well. So, there's scaling up, there's scaling out to disaggregate the ecosystem in terms of having fabless companies, TSMC manufacturing chips for other companies, because the cost of bearing that internally became too great, something that Intel has finally realized. And if we hadn't done that, I don't think we'd have much of a semiconductor industry in this country at all today.
Mike, that's a great introduction. Thank you so much. David, interested to hear your perspectives on the state of the industry and especially on the VC and the finance side.
Great, thanks, Stephen, and thanks to ITIF for having me today. Really appreciate the opportunity to speak with you all. So my journey into semiconductors was a little bit different. My father started a company called Lam Research, which is now one of the largest manufacturers of equipment in the world. And so I grew up around this industry. That being said, for the first 15 years of my career, I did everything except semiconductors. And it really wasn't until about 2010 that I started to get back into the industry. And that was really driven by the rise of AI in semiconductors and the impact that was having on the entire ecosystem. But before we get into that, what I've observed in terms of the industry, because I've always been following semiconductors, even though I was not investing in this particular market, was that up until that point in time, a lot of the venture capital invested in semiconductors had mixed results. There were a handful of investors who did quite well, but it was a very difficult market as a VC to invest in, I'd say, prior to 2010. And that was primarily because a lot of the innovations that Mike talked about, that we've all read about, were able to be achieved certainly by a handful of new companies, but largely by established players. And you saw the strong get stronger. Occasionally they'd slip up and someone else would step in. But as a venture capital investor, it was a very difficult market. And if you look back at the funding sources during that period of time, before AI really started to come into devices in the early 2010s, a lot of that investment came from corporate strategics, which continue to support the industry, and where almost every investment that I've made over the last 15 years has one or more corporate strategics involved. But as venture capitalists, when the innovation wave of AI started to come in, that really started to change the industry, and it made a lot of the economics very attractive for venture capitalists to come back into this market in greater numbers and support these companies. Stephen mentioned earlier the enormous cost to develop the most advanced processors. I think, as many of you know, the world does not run on 2-nanometer processors. There's quite a lot of processors that are run on older technologies, and those are frankly a lot less expensive to bring to market. And as a venture capitalist, when we do our cost benefit, I am invested in some of the AI chip companies that are investing the amounts that Stephen is mentioning, but the lion's share of investments that I've made in my career are in more mature nodes where you have innovative new designs that are bringing new capabilities to market, but not necessarily pushing the envelope on the manufacturing side. That being said,
while you're on that point, David, just for our listeners, if they don't know, could you just spend a second there? Just what are the legacy of the mature nodes versus the cutting edge nodes to help our viewers understand?
So I'm by no means an expert on the manufacturing side. I think we have a few folks on the call here who on the webinar who can speak about the economics of manufacturing. But as a startup company looking to build a new semiconductor design, a new semiconductor, you are designing semiconductors to be produced at a particular in a particular geometry that is correlated with a cost. And what that, as you get into lower geometries, smaller geometries, the cost increases almost exponentially. And as you're in more mature nodes, more older technologies for manufacturing, the costs are much less. And so, as AI has come into the industry back in that early 2010s, what I started to observe is that you had new designs that were coming in, new designs that the existing industry really was not focused on, because this wave was taking place. And that was where I started coming back into the market, was investing in chip companies, some that were developing processors, some that were developing sensors, others that were developing power devices, but very quickly also realizing that the innovation wave was pushing further upstream. And new materials were required, because there was greater demand for energy efficiency that we're all reading about today in daily life. Was pretty apparent almost a decade ago. And so you started to see innovation on the materials with compound semiconductors that became much more conductive for energy, for instance. But more difficult to handle, and had more impurities. If you look at silicon, which we can all, if we go to a beach, you've got the source product for silicon. That's great. However, if you're looking at silicon carbide, which is used in most electric vehicles, that is the third hardest material on Earth. And so there's different manufacturing processes that are needed to handle these different materials that again give you so much better performance on the other end. And so I started to look at and invest in that particular market. And further upstream, there's also new manufacturing technologies that are coming in to the market that are designed better to handle some of the newer requirements for semiconductors. And so those are some investments that I made as well. And then all the way up to equipment, where I've had the opportunity to invest in a number of equipment companies and be part of that journey. So this innovation wave that from a venture capital standpoint, this innovation wave that really initially was for venture capitalists was very much focused on a small subsection of that $600 billion market that Stephen referenced earlier, which, by the way, was a lot smaller 10 years ago, has now grown to the point where the innovation wave is hitting every aspect of that $600 billion market. And that just creates a whole new set of opportunities for venture capitalists. And I think we would all agree that the AI journey is not over yet. If anything, it's just beginning. And so as a VC, this market offers tremendous opportunity. I would add, as sort of a final point here, that the two things. Number one is that a lot of these innovative technologies require an ecosystem to advance. When we're talking about competitiveness, innovation in this market, it is not only the startups and that designing new integrated circuits, or established companies like some of the ones we have on today that are developing the bleeding edge technologies, but it's also working in partnership with that entire ecosystem to take these products to market, including all the way upstream to the actual equipment that's sitting in the fab. And so that's where, as an investor, I'm most excited. And I think that we're just beginning the golden age of semiconductors, and it's been a journey, but VCs, I think, have a great opportunity here, and I'm certainly glad to be part of this industry.
David, that's wonderful. Thank you so very much. Nick.
Yeah, thanks, Stephen, and thanks, Mike and David, for your comments. I think it actually lends really nicely into kind of what I wanted to focus on in my remarks. David, you just mentioned that, the importance of the ecosystem. And that's something I really kind of wanted to focus on. I wanted to start off by underscoring where TSMC sits in the broader tech ecosystem, kind of highlight a little bit of the economics and the scale that these types of investments require, but really hope that the key takeaway is that, we can't do this by ourselves. The ecosystem has been built over decades. It's incredibly diverse and interdependent. There are hundreds of companies that participate in it, up and down the supply chain, from companies like NVIDIA, who's a very important customer of ours, to some of the tool makers like Lam Research, Applied Materials, and others. But TSMC is the world's leading dedicated semiconductor foundry. So we pioneered this pure play manufacturing model, which it's been mentioned a little earlier, but it really allows our customers to focus on driving forward innovation. We've taken a lot of the cost on the manufacturing side, and that enables capital to flow into other parts of advancing the technology. So TSMC is a key enabler of US technological leadership. We specialize primarily in advanced logic chips. They power everything from smartphones to AI systems. They're in the F-35. They're in the supercomputers at the national laboratories. They're in, NASA's Perseverance rover mission to Mars. A whole host of different applications. And because we focus so much on that manufacturing side, we've become a trusted partner for a lot of the US tech ecosystem. We currently make about 12,000 unique chips for more than 500 different customers all around the world. The bulk of that revenue comes from US headquartered firms. They include companies like AMD, Broadcom, Intel, of course, NVIDIA, and others. And then there's a whole, on the design side, and then there's a whole host of end users that we work with pretty closely to, like Amazon Web Services, Google, GM, Tesla, you name it. Our chips are kind of everywhere. I think the other point that I want to kind of touch on with the ecosystem is if you look beyond just our customers and what we're enabling there, we work hand in glove with all of the materials, with the material providers, the software providers like Cadence, Synopsys, the tool makers, ASML, Applied, Lam, KLA. We work so closely with these companies and with our customers to really make sure that we are all in sync on what it takes to kind of drive innovation forward. We can't operate without each other. So that's kind of where we sit in the ecosystem. And then I thought, Stephen, you had asked if we could touch on the scale. So I thought I might highlight a little bit what we're doing in Arizona, use that as an example of the scale of some of these investments. We are building a 4 nanometer, have built, and it's, we're proud to say that it is reached, that it's, sorry, so one step back. So in Arizona, we're building 3 leading edge fabrication facilities. The first one is a 4 nanometer facility that has reached high volume commercial production. We announced that earlier this month. We're really excited about the progress that's been made there. These 3 facilities are, each individually cost somewhere between $20 and $30 billion to make. So the total investment that we've committed to in the United States and Arizona is $65 billion. Just to put it into scale, like what these buildings look like, it's an 1,100 acre plot of land that we are building on. Just the first fab that's operational, there's enough concrete in it to make 10 Empire State Buildings. There's over 15 million feet of cable, wires, and there's more steel than something like almost 1,000 Boeing 777s. So these things are massive. And with that, obviously, with the scale of these investments, there's a lot of cost that is associated. There's been a lot of U.S. government policies designed to help kind of bridge that gap and make the U.S. a more competitive investment destination. Our decision to come to the United States started under the Trump administration, and then we worked really closely with the Biden administration, to make sure that these investments are successful, and we'll continue to do that moving forward with this new administration. The project itself, just the economic impact is quite substantial. We'll be hiring around 6,000 engineers or 6,000 direct employees to run the facilities. That includes everything from engineers to legal and finance and HR and things like that. But the construction side of things has been a massive boon for the Phoenix area. At the peak of our construction project, roughly over a 2-year period, we had anywhere between 12 and 15,000 individual construction workers on site every single day. We've also seen substantial supply chain activity, a lot of investment following TSMC to Arizona, right? These things, as I mentioned earlier, are supported by a very, very vast ecosystem. So we've seen a lot of manufacturers of semiconductor inputs, whether it's chemicals, gases, et cetera, to set up operations in and around our site in Arizona. We've also, things that don't get talked about, but we've had to kind of to work on as we do this. We've worked really closely with the city and state on some of the infrastructure requirements for these types of facilities. There was not an exit off the highway to where we're building, for example. So a lot of, trying to make sure that we're able to get our employees to and from work. We're working with the city of Phoenix on improving kind of the water reclamation system and being able to recycle, upwards of 65% of what we're doing, of what we're using in Arizona. And that will continue to increase. But these are really, really big undertakings, and just wanted to use that to paint a picture of kind of the scale and scope of what we're doing, but would turn it over to, would end there and turn it over to Eric.
Thanks, Nick. Eric.
All right, thanks so much for having me here, Stephen and ITIF. And I have the privilege of bringing up the rear car on the intro, so I get to say I agree with everything everyone before me has said. Very insightful. I'll try not to repeat points and usher us quickly to our insightful questions. I guess I'll start with how did I get into the chip space, and then talk a little bit about what the company I work for, NVIDIA, does. So I'm a material scientist by training. I actually almost went and became a process engineer at Intel, oddly enough, many years ago. And I got into the chip space because in 2005, I was convinced that Moore's Law was about to end. And of course, that was incorrect, but I recently found a soundbite from the early 90s from our CEO, Jensen Huang, who also believed in the 90s Moore's Law was about to end. And so I think that all just makes us another entry in the long line of annual predictors that Moore's Law is about to end. But here we sit now at 2 nanometer or 1.5 nanometer processes, or whatever we're saying the leading edges. And this time it really does feel like we can only go so much further. And that kind of brings me into what kind of a company NVIDIA is. So NVIDIA is a chip design company. That means that we design advanced chips, but we work with partners, most notably, but not exclusively, TSMC, to physically manufacture our chips. And then we work with a whole diverse supply chain to acquire other components, assemble them into platforms, lots of different platforms, depending on the use case. Could be gaming for personal computers. It could be all the way up to the data center scale for artificial intelligence and machine learning applications. Particularly in the chip design space, NVIDIA focuses on a class of chips that are called accelerators. And in particular, we focus on accelerators for highly parallel computing workloads. And so I'm speaking at a level of abstraction. I can bring it down to what people would be familiar with. A couple examples of highly parallel workflows that have been very useful over the past 20 years have been 20 years, 40 years, have been graphics. But more recently, over the last maybe 7 to 10 years, has been a growing understanding that machine learning workloads benefit enormously from highly parallelized computing. And so that has been the transition of NVIDIA beginning in the early 90s, working in the graphics space and focusing on chips specialized for highly parallel graphics computing, and then has evolved into a company that does both graphics and machine learning AI applications. And so that's been what's become more recently, and kind of the evolution that happened there. The reason those are connected to the end, quote unquote, the end of Moore's Law, or at least as an alternative way to improve systems, beyond process improving is that specialization of design presents and has increasingly presented a pathway to improving platform level performance for certain workloads. So, TSMC is working very, very hard to make every single next generation process better than the last one. And at the same time, there are others in the ecosystem, in the design space, for example, also making the designs better. And then we don't have anyone on this call who uniquely specializes in this, but on the packaging side, and I know, Nick, TSMC does some packaging. I'll certainly, some of the best packaging. So certainly TSMC is involved. I said uniquely though. And advances in the packaging space as well, of course, are very relevant for pushing platform level performance to the future. And the reason that I want to draw a connection between all of these things is we talked up at the beginning about a question of cost, a question of investment. You heard both Mike and David mention this. Certainly, Nick and TSMC is very sensitive to questions of cost. And I want to underline this question of cost because it's very expensive, and also the way that it's done is the cheapest way to do this. Right? That's the thing that I think people don't understand is there are other ways to do some of these things and they're even more expensive. And I want to just give an example and talk about the design space because that's what I'm here to talk about, I suppose. When you make an investment in a capacity, say TSMC makes an investment in a capacity, it has a certain cost. And that capacity is meant to produce chips. Some of those chips will work, and some of them will not work. And so capacity and investment isn't just the money you put in, it's also how many of the chips coming out actually work. This is something that's called yield. And yield and the cost of your investment are connected to each other because that's how much the chips cost, right? If I make a certain investment and only 1 out of every 10 chips comes out of it working, that's very different than if I make that same size investment, but 90% of the chips come out working, right? In terms of cost. And so on the design side, there are things that a designer does that influence how many of those chips come back and actually work. There are things that you go through on the design side, simulation of your design. There's a process called emulation where you actually burn it into FPGAs and test the design for the first time. These are all things you can do ahead of time that ensure that when we send a design to TSMC and it comes back and it actually functions the way that we thought it was going to function. Now, that's enormously expensive. But I could also skip those steps, roll the dice, send a design to TSMC, have it come back and not work, and have to respin that cycle all over again. That's a more expensive way of doing it, right? So mistakes are extremely expensive in this space, and mistakes can start all the way back at the design. And so when we say how much it costs, $4 billion for the newest design or whatever that might be, it's very different between firms. Understand that what goes into that design is also eliminating sources of mistakes that will make it more expensive than eliminating those mistakes early. So it's not like we invest in design and that's somehow not connected to what happens in manufacturing. It's all a big connected loop that all has to, in a sense, be co-optimized. And the big challenge is that the co-optimization happens among many, many different players. It doesn't all happen in one firm. It happens with partnerships. And this brings me to a lesson that was mentioned earlier. I think what's cited as a lesson that Intel is now learning, but I won't prescribe anything to other firms. It's that if you don't specialize in this industry and you're at the leading edge, it's very, very difficult to continue to compete. Specialization and the scale that comes with specialization is what allows you to focus and compete in the areas that you'd like to compete in. And that's what has led to a sort of disaggregation and then specialization at all levels of this industry. And the final thing I'll say before we can let us go to questions is, so then why does that mean that it's important to sell into global markets, right? So companies make these investments. And I think that, certainly, I wouldn't use this as an argument, but there's this idea of like, well, the companies deserve to get the benefits from that. They make the investment, they deserve to benefit from that. And I certainly would say that participating in a liberal capitalist economy does contain an assumption of that. But that's actually not the argument I would use. The argument that I would use is, why is it important that firms be allowed to sell into global markets? Because The revenue that comes from that is what feeds this very expensive cycle of innovation, elimination of as many mistakes as possible, competition, and victory in that cycle is not preordained to go to US and allied firms. There are competitors in this space. You can look at the Huawei and SMIC ecosystem. You can look at what they've been able to do in the mobile device space, and you can see that there is an extensive capability over there. It hasn't spilled over into some of the more topical spaces of the 2020s, like data centers and artificial intelligence, yet, but there is no fundamental reason that the US and allied ecosystems have to win in the AI and data center space. It is not pre-written. It is an active competition. We're in the very early stages of it. I know it feels like we've been doing this for years, but I ought to point out that NVIDIA only made more money from data centers than from gaming in 2023. That's the first year. And so this has not been going on for a decade. We're at the very beginning of this. And the ecosystem that is best able to capture the revenue that's generated from global demand and feed that into its innovation cycle is going to be the ecosystem that wins. I do think that the US and allied ecosystem has a leg up in that, but it is not guaranteed to be impervious. And I guess that hits the end of my notes. So I'll hit a period on that and turn it back over to the moderator.
Thank you very much, Eric. Those were good comments. Let me first ask if there was any reaction that any of the panelists would like to make to something they've heard a fellow panelist say here.
I just have one comment to what Eric mentioned here at the end of his remarks, which by the way I appreciate both what Nick and Eric walked us through. I think it was very much an illustration of where the market is today and also where it can go and how early we are in the cycle. But what I would add is that I do believe that this particular in this particular industry, there are the U.S. has a very strong advantage in certain parts of the supply chain, namely in design and in equipment. Those are two sort of undeniable areas. My personal view is that, and I'm not a policy person, so I'll let the policy experts here discuss how this should actually take place. But it is very clear that a lot of the new innovations in equipment are very, very impactful to designers. They allow designers to do things that that have never been done before. And some of those equipment makers may not be in the U.S., but by and large, you see that. And so one of the areas that I'm very encouraged about here in the U.S. is a focus on creating innovation centers. And I do believe that there are going to be some equipment innovations that are going to be enormously impactful to designers, and that will allow a region like the U.S., a country like the U.S., to maintain or potentially extend its lead based on some of these more rapid innovation cycles and perhaps more advanced technologies than others have. And so that I do feel like that's an important piece of the puzzle here as we look forward, not only to be playing defense, but also to play offense in terms of giving designers the right tools and in partnership with manufacturers, of course, to make this happen. The other point I would make, which was mentioned about packaging, and by the way, Nick, I've been to Taoyuan, so I do know that TSMC does have a packaging facility or two or three. And I would just say that the challenge, and Eric mentioned Moore's law. I think as Moore's law is reaching diminishing returns, the challenge is less about putting more transistors on a device and more about putting devices next to each other and packaging them together to deliver what is needed. And that is a brand new market. It's a market that's been around for decades, but not in the way that it's being viewed as going forward, where that is where you will get the efficiencies in power, in processing, et cetera. Whereas before, you could rely on Moore's law and just continue to develop and advance the industry. Now you need to continue to do some of that, but you can't get there without having new ways to actually put these chips together on a platform so that it can deliver what the end customer needs. And so from that standpoint as well, I think that this is a 18-month, 24-month journey that we're on, maybe 2 or 3 years, but it's just the beginning. I'll leave it at that.
Thanks, David. Mike, 25 years ago, there might have been 25 companies at the leading global edge of semiconductors, whether it was logic, memory, or analog devices. Now maybe we're at 10 companies, across those domains. Some have charged that type of increasing concentration is evidence of anti-competitive behaviors in the industry. I think you've pointed out that actually there are more firms than ever now, actually. And we've also noted that this requirement to scale can kind of winnows down the number of firms that can compete at that cutting edge. Others have made the charge that the complementarity between hardware and software ecosystems creates a switching cost that maybe companies exacerbate in anti-competitive ways. Could you maybe walk us through, and Eric, certainly calling you and NVIDIA with the connection between the CUDA system, why is the connection between software and hardware not an example of firms in the sector using anti-competitive practices?
So maybe if I go to your first point of the number of firms, the entire world economy and how we use electronics has changed so much in that time. And so you could say leading firms, but it was different. The way that we use technology, how pervasive it is today, the number of electronics devices that each of us use, that's what's led to some of these huge markets that didn't exist 30 years ago. And so that's why, I think it's a false comparison to look at. You can't just look at the number of firms or what they were doing. You have to look at the entire world of electronics and devices and technology and how it is advanced and how it's being used, and then what it took to make those breakthroughs, as I was saying in my earlier comments, to get to the point where we even have a segment for mobile device processors, or we even have a segment for AI processors. Those didn't exist, and they only exist because of the companies that were able to scale up and how the ecosystem has scaled up at the same time. To your point, and maybe I should pass this off more to Eric, but besides having a master's degree in engineering, I have an MBA, and I worked on the business side as well as the technical side. And the one key point my favorite professor in my business school taught me was what we call whole product solutions. People talk about the complete stack. And I can't even count how many discussions we're getting this idea of NVIDIA's moat with CUDA. And to me, that's not really what it is. What it is that they have a whole product solution, a whole system solution, and CUDA was written to optimize how you use NVIDIA processors. If another company came along and had a whole product solution that was just as good, it would combine the hardware and the software, and we wouldn't just be focusing on CUDA.
Yeah, Mike took the words right out of my mouth. I think that there's a focus on what does it mean to be a dominant provider of a solution, and what exactly is the form and function of what is called a monopoly or what is an anti-competitive practice, right? So I think Mike brought up the point that okay, if we narrowly focus on a single vertical, we can say that is, anti-competitive in a sector, but really it's part of a broad microelectronics sector, even a broad leading edge microelectronics sector. This is a brand new vertical that is basically being built under our feet right now. And so, what does it really mean to be dominant at a point in time in a vertical that didn't exist 5 years ago that's being built right now? So first I'll just lay the groundwork by saying, I don't know if there are clean answers to that, except to say that I think that our understanding of long-term pervasive monopolies in industries that already exist. Like drawing parallels there, I don't think is very helpful. The other thing I will say is, I think that questions of market dominance over-focus on sales versus installed infrastructure. And so if you look at accelerators that are doing machine learning applications, yes, sales focus on NVIDIA chips, but look at the actual chips going in installs. It's lots of in-firm chips because Google has their own chips. They deploy almost at the same scale that NVIDIA chips get deployed at. They just don't sell those on the open market, so they don't get counted as part of that, sector. Amazon has their own chips, right? And so when I look at the total accelerators going into install in these data centers, it gets a lot harder to paint a picture of NVIDIA as the only person, the only entity putting accelerators for machine learning into these. That's the first thing I'll say. So I think just on the face of it, that's not what's happening. But then also, just as Mike said, if there are other firms that come in with complete package solutions, that's what CUDA is there to serve. And by the way, it's also what other elements of the NVIDIA stack are there to serve. It's what the networking infrastructure, it's what the smart optical fibers, it's what all of NVIDIA a few years ago acquired a company called Mellanox that focuses in networking accelerators, right? It's what those are there to solve. It's to be able to provide for customers that want it, a turnkey solution that includes all the hardware elements and the software support that you would need that co-optimizes it. But it's not an ecosystem that says if you buy one part, you need to buy all the other parts. You're allowed to go a la carte with any of the elements there. And so all of those things, I would say, I think chip away at the argument that something deeply anti-competitive is happening here. It just is the case that at a moment in time, there's a certain solution that is expensive, but in terms of total cost of ownership, the cheapest way to provide the answer that people are looking for a capability in AI.
Great. Thanks, Eric. At a speech on his second night in office in Florida, Trump actually took to denigrating the CHIPS Act, which of course provides $39 billion of loans and grants to a number of companies. And in fact, those incentives have already spurred $450 billion worth of private sector investment in the semiconductor and electronics sector. But Trump said, the companies don't need the money. Could one of y'all perhaps explain, what's the logic behind why we put those CHIPS incentives in place? Why do the companies actually need the support with these investments? And how would you respond to the president's critique on that point?
Yeah, I mean, I can talk about the importance of the incentives for a company like TSMC. When we announced our fab plans in Arizona, they were under kind of with the understanding that there was going to be some federal incentives that were not yet in place, but had spoken with a lot of U.S. officials about kind of the cost differentials between building a facility like this in the United States and building one either in Taiwan or elsewhere. Part of it is the scale of the industry that operates in other countries. Taiwan has been building these things for 30, 40 years. You gain economies of scale across the supply chain. And in order to attract and incentivize some of that type of development in different places, you're starting from zero in a lot of ways. So you really need to kind of put that down payment, that jumpstart, that catalyst into place. And I think the CHIPS and Science Act did that. And as you mentioned, there's been quite significant results in terms of real dollars invested in the United States from that. So we're hopeful that that these programs will continue. I think that yesterday in his confirmation hearing, the nominee for the Secretary of Commerce talked about the importance of chips being a down payment on these things. So, we're going to continue moving forward. We think they're incredibly important programs.
Great. Yeah,
I would just point out that all the money isn't just going to corporations. They set up a number of these technology centers, like David mentioned, One of them is at my alma mater. And so I think that's critical for building that foundation going forward too.
Yeah, $11 billion for research, stood up a National Semiconductor Technology Center, National Advanced Manufacturing Packaging Facility, a new Manufacturing USA Institute on semiconductor digital twins. So really a robust set of investments in the industrial economies behind the sector.
Yeah, I wanted to tug on that. I'll try to go for 1 minute, which is apparently difficult for me. Because David said something earlier that we then went to a new question and I wanted to touch back on, but I think it's relevant to this because David's point was, look, we are quite far ahead in certain areas of this. And yes, there's an element of needing to bring back what has been lost, but we need to not forget that we also need to maintain leadership in the areas where we're strong. And I think, David mentioned the equipment and design space. I think he's absolutely correct. And yes, there are very innovative equipment firms that aren't US. But, I think that part of that as well, and part of the answer to the, what's the value of the Chips and Science Act is also making sure that, yes, part of it is to try to incentivize to bring back what's been lost, but make sure we double down on those areas that we know we have a strength in for 2 reasons. First is that the strength is not permanent. It is something that you have to reinvest in to maintain. That's first of all. And second of all is because those strengths actually are the things that come from the areas that our society actually is designed to be best at, which is freedom of movement of information, creativity and innovation, leveraging our very strong and best in the world university and innovation center system, right? And so it leverages those and it reinvests in those, and that's a very important part of this as well. Maybe not for the battle for capacity of 2026, right? But for the battle of who is winning this over the next 20 years, it's critical.
Yeah, absolutely. David, I love your perspectives here. It's been a critique of the U.S. venture capital system over the past 50 years or so that it's really excelled only for 2 sectors, software and biopharmaceuticals. That it really hasn't been as effective for what some call deep tech, things like clean energy, hardware, semiconductors, physical things. Has the evolution of AI now kind of melding the software hardware together, which is what's changed that? And also globally, how is the state of VC flowing into the semiconductor industry in the US versus say China or elsewhere?
So I would say that certainly, certainly in terms of venture capital, this particular industry is not necessarily as easy to integrate into a venture capital practice as, say, software. And the reason is because by definition, semiconductors is multidisciplinary, right? I think everybody on this call, including myself, has different engineering degrees of various types, and we all understand a piece of the puzzle, but it's hard to have enough education, so to speak, and domain expertise to understand every aspect of this entire industry because it cuts across so many different academic areas. And so as a venture capital firm, we're always looking to be the most efficient with our time. And if I can evaluate a software company or an internet company and do so in an ecosystem of people who can very quickly get up to speed and also, frankly, from a public market standpoint, have had very, very strong returns over many, many years, VCs are going to be drawn more to those types of investments. And as I said earlier, I spent the first 15 years not investing in semiconductors, and I was actually in software, and I think it's an excellent market. I think now the opportunity in semiconductors, because of the innovation cycle, is creating disruption across the ecosystem, and I think that creates some new opportunities. VC firms, however, do need to continue to adapt and be able to prosecute these investments that are fundamentally have different business models compared to software, have different domain expertise to understand the technologies themselves, and also different social networks of people who understand the sector and are innovators in this sector. So I think that's still a journey. I am encouraged by a lot of the corporate strategic investors, right, including those on the webinar today, that have active investment programs And I think they are a key part of this solution because, again, unlike some other sectors, this is a very interdependent industry. And so there's a lot of value that can be brought in from multiple strategic investors into any particular venture-backed company. But if you look at the amount of dollars going into venture capital, from the venture capital industry into semis relative to these other sectors you mentioned, it's still very small. So it makes my job actually a little bit easier because I don't have as much competition. We just talked about monopolies. I certainly don't have a monopoly on this sector, but it is nice to have, about 10 or 15 other firms in the industry rather than 10,000, which is basically the number of VC firms in the US. And I can barely count 15 VC firms that focus on this sector. So it is good to have less competition, but it's great it would be great to have more investors in this market.
Great, thanks. Well, most viewers will know that the industry had shockwaves sent through it early this week when a Chinese competitor called DeepSeek introduced a large language AI model called R1 that they claimed they were able to train with about $6 million investment. That was far less than the $100 million of commonly quoted for such systems. The observers seemed to think that the system was comparable to Claude, ChatGPT, etc. So we have a question from the audience. Does increased AI model efficiency actually reinforce infrastructure monopolies? If so, what does that mean for meaningful competition in the US AI ecosystem? So maybe take that question and then add your perspectives on how the industry looks different later in the week after DeepSeek has come onto the scene.
Okay, answer is no. Quite the opposite. Quite the opposite.
I completely agree.
Yeah, no, I mean, first of all, the fact that they did it on less than the highest performance NVIDIA processors demonstrates that you could use different types of systems to do it. And, whether that ended up being something that they build in China, and there are AI processor companies in China, or it's a domestic competitor to NVIDIA, it actually increases the possibility of doing that kind of work on other companies' hardware. But there's we would need hours, and I've already spent hours elsewhere talking about this, to actually understand what happened here. And it's an optimization of a model that had already been created with somewhat more limited capabilities. And people shouldn't get overly excited that this is a complete change in how we develop large language models. And anybody wants to contact me afterwards, I offer my consulting services to go into deeper time on this.
Yeah, I completely agree. It's very weird to look at a market delta of the magnitude that we saw this week, and your response be, I just don't think anything has changed. And that's, or if anything, quite the opposite. I think that an example of a very impressive model that, as we understand it, is not only an optimization of a pre-existing model that was infirm, but also that used interactions with the API of closed source models to further optimize their model, as evidence that you can use open and closed sourced AI models to optimize existing models or help create new variants of models, even on denigrated hardware, is great news. It means that our ability to create pared down models and operate them efficiently is much more promising. It means that there's a much greater likelihood that we'll be able to put pared down models in edge and autonomous systems. It's huge for robotics. But let's not also forget that the model that was developed is not a truly frontier model. It competes with publicly available, impressive chain of reasoning models, but it's not ChatGPT 5, right? And so I think the lesson that you can take more advanced models and use them to create highly efficient but not quite frontier models is excellent news. And it's not just excellent news for the technology space, it's excellent news for users because the tokens are less expensive, the economic use cases you can bring it to bear on are therefore broader. It's good news all around. I would, I'm not an investment analyst or advisor, but I wouldn't read in too deeply to the immediate knee-jerk reaction that I think was based on a poor understanding of what had actually happened.
Yeah, I would just add a quick thought there, which is that from an investment standpoint, it does bode well for developers downstream. Whether you're building a semiconductor that sits, like you said, in a car or in a watch or in a phone, and you still want to run some of these models, having that innovation take place is huge. I also believe that there are a number of software companies that have very interesting models that they want to run but can't afford to run. And by lowering the cost for them to do that, you're accelerating innovation at the software level in the enterprise software space. And I think that's very beneficial as well to end users. And I think we all know from having been in this industry for a while, at the end of the day, someone is using your technology to do something. And if it costs them less to do it, and they can do it more easily, and they can do it faster, that is always a benefit to the semiconductor industry. So I see it as a net positive, although I think that it does, for software makers, probably take them for a bit of a loop. And there's some infrastructure folks who are probably looking at how they're allocating their funds. But I think in the long run, this is great news for the semiconductor industry for sure.
Okay, we're just about at the hour, but since we have several more questions from the audience, we'll go for about 5-10 minutes more to take those, and then we'll wrap it up. We talked about again scale and the need for companies to be able to sell their products into global markets, to recoup revenue and to be reinvested to finance future generations of innovation. But in the final week of the Biden administration, it released a new export control framework for artificial intelligence diffusion. This would essentially divide the world into 3 tiers of countries: Tier 1, Tier 2, Tier 3. About 18 or 20 countries in Tier 1 could have receive unlimited exports of U.S. GPUs. So the Tier 2 countries would have some caps, and then Tier 3 competitors would be excluded. I wonder if y'all could comment on the framework for AI diffusion here, and one of the things it does is say at an aggregate level, the U.S. cannot export more than half of its GPU power. How should we think about this framework? And there's an opportunity now to comment on it. What are your responses?
I think I'll at least just, NVIDIA published a blog post about this, so I can at least agree with that. I think that both from inception and how implementation would go, I think this is a poorly thought out rule. I understand the framing has been that it somehow keeps chips out of the hands of China, but this rule does nothing to ratchet up export control on China. It's targeted at the rest of the world because there's a presumption that China is accessing chips that is actually said to be going to the rest of the world, but it's somehow going to China. I think that the documentation of the DeepSeek model being trained on H800s and H20s, which are chips only designed for China, is evidence that that's not really what's happening at scale, or at least it's not a key enabling part of what they're using for their AI ecosystem. And so the problem that it's trying to solve doesn't seem to be a huge problem. And the problem that it creates is that now there is a potentially enormous unaddressed global compute vacuum that a US or allied, we'll see how broad the rule can go, or allied chip provider is not allowed to address, but is by law not allowed to address. And if I was trying to think of the ingredients that would go into a recipe to make Huawei and SMIC as powerful as I possibly could, this would be one of the key ingredients. It would be to create some captive global demand that can only be addressed by Huawei, which is what this starts to go down the path of doing. So there's a lot of other tactical responses I would have about how this is difficult to implement, things like that. But I want to push all of those aside. Understand that countries like Poland, Israel, Iceland are among those that are not allowed to receive US chips beyond a certain capacity. Those are not countries that we want to be creating an incentive to purchase Chinese ecosystem chips within. To say, oh, if you want chips beyond this certain amount that the US government has decided, you'll have to look elsewhere. Those are not countries we want to be sending that message to. Not to mention intermediate countries that we are always concerned about the balance of technology power and whose ecosystem they might tilt towards. So I'll just at a very high level, I think it fails on the immediate sniff test for that reason. But that's my NVIDIA perspective, so I'll pause there.
So maybe offer a slightly different perspective on it. I can totally understand how the likes of NVIDIA, and I've heard Oracle on this and others, would react to the specifics. I've taken a slightly different way. I mean, I'm not involved in government at all, really, but I would expect that the Biden administration realized that the likelihood of this actually getting enforced was probably pretty low with the change of the administration. And so I don't get too hung up on those specifics because I'm not in a company that's going to be affected by it. I look at it, what I actually read through, as difficult as it is to do, a 160 plus page document. And I was impressed at the technical insight that it reflected. I was not expecting that from a document written by anybody in government, sorry. And so I think the value of that document is in the attention that it's gotten and raises the question of what should our policy be, that regardless of who builds the system, this technology is advancing so quickly that it could, and people like Altman from OpenAI have talked about, there are potential dangers here. And we need to have a strategy on how we're going to address that. And I think Oracle rightly said that it should be a partnership between the experts in the industry and government. But that's the value in that document to me.
I think certainly to the extent we have those in government who have a much more sophisticated understanding of these technologies and systems, that is very important to facilitate these partnerships with industry. But though, ITF has written, you can see on our website that we believe that the rules were well intended but overwrought, and will need some modification in the current administration. Okay, let's take one final question, and then we'll wrap it up. So the question is, which area of semiconductor R&D is the most critical for maintaining U.S. competitiveness in the industry down the road? I'll just invite you each to close with that, or maybe with a final comment that you might like to offer. Thank you.
Wow, I don't think I could pick just one. I mean, as David said, the industry is hugely diverse and multidisciplinary. I would just say that we need to have a lot of support for R&D, because the new ideas will come from the universities and research that we haven't even thought about yet. It's important that we maintain and support the technologies that we see that are revolutionary today, but we can't anticipate. I could go through other technologies, et cetera, that are just at the early nascent stage, but there are just too many to talk about.
Yeah, perhaps I'll just give an example of where I think that it is important to have an ecosystem view, and competitiveness is, as Mike said, it's hard to just focus on one area versus another. When you look at these, for instance, on the design side, you have for those who are pushing the envelope, they need to know where they can innovate, and there's so much change happening in the industry, whether it's manufacturing, materials, and equipment. You really have to have a holistic view. So I think we've talked a few times already about some of these innovation centers that are being established in various parts of the U.S. I think that is very, very critical to maintaining and actually enhancing U.S. competitiveness. I don't think you can just focus on one area or another. I don't think you can just say, I'm going to focus on IC design and that's it. Nobody else, will create 10 NVIDIAs in all the different areas where NVIDIA doesn't focus on and be done. You can't do that because the innovation cycle has to hit all these other parts of the supply chain. And so that's why I also feel that the advanced packaging focus for a lot of these design centers is very important as well, because only by putting all these pieces together can we truly innovate and also access these. I think, as Eric mentioned, these parts of the U.S. society that have been doing for decades what they do best, which is design new material, design new systems, and design new semiconductor devices to deliver capabilities that customers want. And so I think having that full view is important. And I think I see a lot of innovation. I've invested in a lot of innovation across that entire ecosystem. And I think a lot of those companies are very excited about being involved in these public-private partnerships that can help advance their cause, because they're small companies. They don't have access to the resources that an NVIDIA does if they're a designer. If they're an equipment maker, they don't have, they're not getting calls every day from TSMC, or NVIDIA can pick up the phone and call them and they'll hear someone on the other line. You really need to amplify that innovation ecosystem so that everybody is aware of what's the latest and greatest. And I think if they are, the market forces here in the U.S. will create a very, very competitive semiconductor industry that'll be around for a long time.
Yeah, I'll say three things. Agree with Mike and David. That's not one of those things. Zero thing. I agree with Mike and David. I'll say three things. One of them is the U.S. cannot afford to ignore fields, because the nature of breakthroughs is that it's very difficult to predict which field or subfield a breakthrough is going to come from that's going to suddenly cascade throughout the entire technology stack. And so we must invest across all of these fields, as these guys have said before. In that same vein, it's difficult to predict which country's ecosystem of breakthrough is going to come through. And that makes collaboration with our supply chain and geopolitical partners really, really important, because we want to make sure that we're capturing as much of the allied innovation space as we possibly can to jointly push a leading edge advanced technology space, right? So that collaboration with our partners in the semiconductor space, certainly, but you can point to adjacent as well, very important. So that's number one. It's hard to predict where breakthroughs are going to come from. Number two, if I look at the pipeline of innovation, it all begins with early stage research. US government funding of early stage research as a percentage of GDP is about as low as it's ever been since World War II. That is a long-term problem. That starts to introduce a constraint on the pipeline of innovation into what eventually becomes technology, and it's one that ought to be addressed. The Chips and Science Act had a whole and science part that mostly wasn't appropriated. So that's a challenge. And so when I think of areas that we ought to be thinking about, we should take our eye off that ball. And then finally, and this is a part that the Chips and Science Act, I think, did focus on, and that David mentioned in these sort of regional innovation hubs, is how do advances made at the basic and applied research transition into technologies? Well, there's this thing called the Valley of Death where ideas go to die. I used to work at DARPA. Every single program I've ever worked on, except for like one, created a prototype that went and sat on a shelf, never to be touched again. It's a really cool piece of technology. It's not being used, right? And so how do you cross that? How do you transition it? Part of it is, how do you teach professors about this? Part of it is how do you help prospective customers learn about what's happening in the space? There's a lot of ways you attack this problem. These regional innovation engines help with some of that, but that is an area that needs continued investment because it's not clear whose responsibility it is. Is it the government's responsibility? Is it private industry's responsibility? It will never be clear whose responsibility it is. That's always a tug of war, but it's one that always needs perennial attention, because that's when we invest in ideas, they reach a certain level of maturity, and then there's a make or break moment that's right there. And that's where a lot of ideas go to die, even if they're great ideas. And so I'll put a pin there, but broad thoughts on that.
Invest and collaborate. That's what America does so well. All right. Well, Mike, David, Eric, and Nick had to drop, but to him as well, thank you all for being with us today. Really appreciate your excellent insights and remarks. This video will be available online to socialize afterwards, and we look forward to continuing to collaborate with you all to drive U.S. competitiveness in the semiconductor space forward. Thank you for your time today.
Thanks, Stephen.
Thanks so much for having me.